Just a spacecraft that is going to go and smack an asteroid. It is fantastic to see it in real life. DART will only be changing the period of the orbit of Dimorphos by a tiny amount, and really that's all that's needed in the event that an asteroid is discovered well ahead of time before it might impact Earth. You can't have a mission like DART without finding the asteroids first. That involves searching for near-Earth asteroids, getting them in the catalog, calculating their orbits, tracking them, keeping an eye on them. You know, as a kid, I loved astronomy, I loved Star Trek, and so I became a research astronomer. My first observing run ever was observing the impact of comet Shoemaker-Levy 9 with Jupiter. I never would have known that somehow my career would kind of come full circle to be part of something that affects people's everyday lives. I feel really honored and humbled to be working in the field of planetary defense because it can affect people. It's just really exciting to have that kind of role in an area of science that has such a broader impact, you know, figuratively and literally.
Hi everyone, I'm Josh Handel, and I'm a public affairs officer here at NASA, and I am so excited to be joined today by Dr. Kelly Fast, who you just had the opportunity to meet. Kelly, thank you so much for joining us today.
Oh, thank you, Josh. I'm glad for this opportunity to answer some questions.
Kelly's here to answer all of your burning questions about planetary defense at NASA and the DART mission. If you have a question you'd like to ask, send it in using the hashtag AskNASA or by writing in the comment box wherever you're watching today's broadcast. So, Kelly, in your video, we learned a little bit more about your role with NASA's Planetary Defense Coordination Office and the DART mission, and you have this really great line that says, we need to find asteroids before they find us, so if we need to, we can get them before they get us. Can you tell me a little bit more about why that's important, and specifically for a mission like DART?
Well, sure. I think it was Don Yeomans who coined that phrase, find them before they find us. And then so I kind of added to it with get them before they get us. But even though DART is a very important test here to try to get some tools in the toolbox, should an asteroid ever be discovered that does pose an impact threat, we still have to do that other side of the coin, which is really the primary mission of finding near-Earth asteroids. And so the program at NASA, the Near-Earth Object Observations Program, funds projects to take telescopes every night, surveying the skies, looking for new near-Earth asteroids and calculating their orbits. Telescopes like the Pan-STARRS telescopes at University of Hawaii or the Catalina Sky Survey at University of Arizona. Other telescopes, both funded by NASA and then also observatories around the world continuing to follow up those discoveries in order to fill out the catalog so that we even know if we would ever need a technique like DART to divert an asteroid. And you'd want to know that well ahead of time. And so that is why you'd want to find them well before they find us.
It's a great answer. Thank you, Kelly. All right. Well, all of your questions are starting to fly in, so let's get started. As a reminder, if you have a question you'd like to ask Kelly about planetary defense at NASA or the DART mission, send it in using hashtag AskNASA or by writing in the comment box wherever you're watching today's broadcast. So, Kelly, Zach Burnett on Twitter asks, what kinds of light curve modeling are done on a mission like this? Because from what I understand, resolving power of optical telescopes usually isn't enough to resolve asteroids. So how do you infer the geometry without directly observing it?
Well, that's a good point because the asteroid system, Didymos, is going to pass Earth well away from Earth, but it's a chance to look at it with telescopes when DART impacts. And that is going to be how we determine what happened after DART impacted the moon of Didymos. But it's still so far away, like it was mentioned there in the question, the resolving power is small. And so you just see this point of light, but this point of light gets brighter and fainter and brighter and fainter as that moon of Didymos, Dimorphos, goes around Didymos and passes in front, passes behind. You see the two together, you see one blocking the other. And so that's why the light goes up and down. And so the period with which that light goes up and down, which represents the time of that orbit of the moon around Didymos, that is what will be changed by DART. DART will impact Dimorphos and just change its speed slightly. And so that will change that period. And so in telescopes on the ground, yes, they can't resolve the individual asteroids, but they can look at that combined light. And through modeling, the astronomers on the investigation team will do a fantastic job of backing out that information to be able to assess what effect did that DART impact have on the orbit, and then essentially on our capability to be able to deflect an asteroid of that size regime should we ever be faced with that need.
That's a good point, Kelly. And you do mention that we are going to a binary asteroid system and actually targeting the asteroid moon. So I would imagine that's important for this experiment.
Right. This is kind of a nice opportunity that nature has given us to be able to test like a technique in like a laboratory setting. By having a binary asteroid like this, it's much easier to detect from the Earth what an impact like DART might have on the orbit of like the moonlet around the asteroid Didymos, rather than trying to test this just changing the asteroid's orbit around the sun. In fact, an impact like DART will have very little or no impact in that sense, no change. But it's that orbit around Didymos by the moonlet Dimorphos that will be affected, and that is much easier to measure in this binary asteroid system. So everything kind of comes together where Didymos just kind of kindly comes to the right position where telescopes can just watch from Earth and see what that change is after DART has its encounter. And that information will feed into understanding the kinetic impactor technique in general, and the DART team and the astronomers on the team will communicate and feed all that into their modeling so that they can turn that into some real results about what we could expect should we ever need to design a spacecraft to do this for real. The nice thing about the Didymos system is, it poses no threat to Earth. We couldn't even make it a threat to Earth. It's a wonderful laboratory that nature's kind of put right at the right place, the right time, where we can use this combination of ground-based telescopes and the spacecraft to do this experiment, which is great because it's nice to do this at a time when we don't need it, just so if there is a time that we need it, it's not the first time we've ever tried to kind of test some of the techniques that might be in the toolbox.
That's a very good point. And I think you actually may have answered Jeremy Deutsch's question on YouTube, who asks, what if the impact test makes it accidentally go more towards Earth? So Kelly, is it at all possible that DART can somehow redirect the asteroid moon Dimorphos toward Earth?
Nope, all it will do is just change the speed of the orbit of Dimorphos slightly, change the period of the orbit. It's still going to be in orbit around the asteroid Didymos. The system will still be in the same orbit around the sun, and we couldn't change it in a way that would make it threatening even if we wanted to. And so, again, this is why this is a perfect kind of laboratory setting, a perfect way to be able to do this test because there is no threat there.
So Mandy Lane on Twitter asks, have you ever had the idea that you should slow down the asteroid to the point where it stops moving instead of altering its trajectory?
Well, that's interesting because, again, trying to change the speed of something in space, that takes a lot of energy, and you don't have to. It wouldn't be possible to just stop something altogether or have it go the other direction around the sun. Everything's moving very, very fast in space around the sun. But it doesn't really matter, because all that matters is that relative motion between an asteroid that could pose a threat to Earth and the Earth itself. And so all you would need to do is deflect it just enough so that it doesn't hit Earth. You wouldn't have to worry about like stopping its motion altogether or changing it a large amount. You only need to do it the amount that you need to so it doesn't hit the Earth. And then and that's important, because the more energy that's involved in changing an orbit, that's a larger launch vehicle, larger spacecraft, and it might not even be possible to do a large change. But all we need is whatever change might be needed in the event of an asteroid threat. Just need to deflect it enough so that in the future it doesn't find itself in the same place as the Earth.
And I would imagine, as you said, that's why it's important to find them early, right? Because the further away it is from us, the smaller of an impact would be needed.
Right, and that's why NASA funds survey telescopes to be operating every night to survey the skies, looking for moving objects against the stars, and determining that, yep, these are new discoveries, or okay, here's one, and we're seeing it again from a few years ago. Building up the catalog and calculating the orbits so that we know where they are in the future. You know, of all the asteroids out in the asteroid belt, but it's the ones that come into Earth's neighborhood that we want to keep an eye on. And the nice thing is many near-Earth asteroids never even come into Earth's vicinity. But there's a class of near-Earth asteroids that come into the inner solar system that actually come close to Earth's orbit. And so we want to keep an eye on those. And then also but continue to discover the ones that we don't know about. That's the bigger concern, because there is no known asteroid impact threat to Earth, that could cause damage that we would want to worry about sending a spacecraft out, which is fabulous. But we want to make sure that we continue to survey for asteroids, utilizing telescopes on the ground, utilizing a telescope for space use that is being developed called the Near-Earth Object Surveyor, trying to bring all the capabilities to bear to continue filling out that catalog, just so we know, do we even need something like a mission like DART or some other deflection technique. And again, you want to do that if there is something that poses a future impact threat, you'd want to know years or decades in advance, because then you don't have to deflect it very much. And you can use some of these kind of more fundamental techniques of just like an impact. And that would be enough if you had years in the future that you had that time ahead of time to work it.
Absolutely. So Matthew on Twitter asks, what experiments were done on Earth to simulate DART's impact on Dimorphos?
Well, there are researchers who work in laboratory settings who who do actual impacts with boulders. They do studies on meteorite materials. They take things that simulate asteroids and do impacts in the lab. And so that tells you so much. But to actually do this with a real asteroid, it's important to really understand what are the properties and what are the extra factors there. I mean, we know physics with perfect objects, but to have an object impact an asteroid and then to have that material blow off the asteroid for something that has like rubble on the surface, which might give it an extra kick, just like if you're standing on a skateboard and you threw a baseball, it would send you in the other direction. I want to understand those properties of not just the impact, but what happens afterwards, and how that all adds up so that that can be understood. And a lot of that happens in the lab and in the modeling community doing calculations. And this will be a good test of all of that.
That's actually a good segue into our next question. That comes from Khaled Zubi on YouTube, who asks, will the orbital debris after the collision endanger any of the satellites sooner or later?
Oh, this is so far away that no, this does not pose a danger to satellites on Earth or to anywhere, because this is so far away. So that's not going to be a problem at all. If anything, there's more. We have meteor showers every year when the Earth comes around the sun and goes through debris from a comet's tail, and we have the occasional meteoroid that enters Earth's atmosphere. You see a nice fireball. That's happening all the time anyway, and so this is not going to add to any of that.
Simon Taylor on YouTube asks, what is the percentage chance of us meeting the possibility of having a life-threatening asteroid strike in the near future?
Well, the nice thing is this is a very rare event, and hopefully we'll never even have to deal with this in our lifetime, in our children's lifetimes, grandchildren's lifetimes. But we still would want to search and know, even if something like an asteroid impact that could cause like regional damage on the Earth, it might be like a once a millennium type event. Or even something like the Chelyabinsk impact over over Russia in 2013, where a small asteroid disrupted in the atmosphere, and there was a shock wave, and it still did damage on the ground. And so that was kind of the most serious thing we've seen, and that's maybe a once a century event. And so it's so rare. Hopefully, we'll never even deal with this in our lifetimes. But again, we still would want to look just so that we know, and so continue surveying the skies and cataloging those objects, just so that there is no surprise, and so that we might know statistics and be able to infer from the geologic record, but we still need to look just to know.
Absolutely. We need to know what's out there before we can potentially mitigate anything. So Michael Kilgore on Facebook asks, if DART is successful, would it help enable NASA to deflect larger asteroids? If so, what is the largest asteroid that could be redirected?
I'm not sure of that answer offhand, but certainly in the size regime, Dimorphos, the satellite of Didymos that is going to be impacted, is about 160 meters in size, and that kind of represents the sort of the size range that and larger with which Congress has tasked NASA with, finding these asteroids, because these could pose a regional damage threat to the Earth should one impact. And so the nice thing is that for that size, a technique like DART, could be very effective, which is why this is being tested. If there were asteroids that were much larger, something that posed an impact threat that was much larger, or if there was far less notice so that it wasn't possible to divert it with the kinetic impactor technique, there are other techniques that can be utilized. In the case of, if there was a lot of warning, there's some other techniques like a gravity tractor, just using gravity in nature, having a spacecraft sitting next to an asteroid and kind of letting the spacecraft tug on the asteroid with the natural force of gravity, or enhancing it by picking up a boulder or what have you. That's just another technique that could be used with long notice. There's also, you see it in the movies, but never quite the right way. For instance, nuclear deflection is used, but that really, the goal wouldn't be to blow something up. Again, it's all about deflection and just nudging it off its path. And if there's something that is very large, it would be possible to use a device to do a deflection. So there are other techniques that can be used, but the kinetic impactor technique, can be used with the asteroids that are toward that smaller range. That actually, there are far more of them, and so that the odds are that if something ever did pose an impact threat, it would probably be in that size range. And so that's why it's nice to test this technique, but then continue modeling with the other techniques, so that if they are required for larger size, that's something that has been studied. So again, there's no one solution, but you try to do studies in all areas just so that you're prepared and you have a nice toolbox to work with.
And for those just tuning in, remember to send your questions in using the hashtag AskNASA, or by writing in the comment box of wherever you're watching today. So Kelly, Robert Nolan on Facebook asks, before this process goes down, do you believe it will move the asteroid significantly?
No, in fact, we really couldn't. As you saw in some of those animations, the DART spacecraft is far smaller than this little moon, Dimorphos, and certainly a whole lot smaller than Didymos. And the goal isn't to move it significantly; it is just to test a deflection technique and to change the period of the orbit with that impact. Because again, that's all that would be needed in the event of an actual impact threat, just to be able to divert it a small amount. And so as you can see here, the size difference is pretty large. And so the change in the speed of the orbit is also going to be small, of the orbit of Dimorphos around Didymos. But again, that's all is needed. We don't need to do a large deflection, and especially for this to be able to get the data on what comes out of the first ever planetary defense test. This is just going to be really valuable and then useful for modeling other cases, where maybe something larger is needed. but it isn't going to be a large deflection here, but certainly a significant one that can be measured from Earth. That's the plan here, and folks are gearing up for that to be ready to watch that.
So speaking of watching things, Eldora on YouTube asks, does the spacecraft have a camera to record the impact?
Well, it has a camera actually to guide the trajectory. So it's a very simple spacecraft, with what it needs to be a spacecraft, like solar panels to generate electricity and the other instruments needed for it to actually navigate to where it needs to go. But that camera is to make sure that it can line up on Dimorphos and impact it, which is done autonomously. There's some fantastic computer work that's done to make sure that it can line up on itself, because this sort of thing can't be commanded from Earth because of the light delay time. So it's going to line up itself based on that camera. And so that is going to be all for tracking to the asteroid. The Italian Space Agency has contributed a small set called Lucia Cube that is going to actually take an image of the impact, but it is going to continue past the Didymos system after that happens. So it will capture that, but then after that, it will be the telescopes on the Earth that will have to look for a longer period of time to determine what sort of change was made in the period of the orbit of Dimorphos about Didymos.
So Orbital Plausch on YouTube asks, how will the Lucia Cube improve your analysis of the impact of the DART spacecraft?
Well, certainly just getting that look at the impact, that would be really valuable, and whatever might be captured during that short period of time that Lucia Cube will be continuing by the Didymos system. And so, just any view will be really valuable for seeing if there is much in the way of impact ejecta from the impact, and any material coming off of Dimorphos. So that will still be very valuable for understanding what actually happened and turning that into modeling that can be used to understand in general how kinetic impactors and the interaction with asteroid material, how that works.
Harmony X on YouTube asks, how will you know if your impact actually alters its trajectory significantly?
Well, and that's where the astronomers on the ground are so important here, with having large telescopes looking at the Didymos system and looking at that light coming from the system, which will be going kind of up and down in this light curve as those two asteroids revolve around each other. And the folks using the modeling here can kind of back out from that, how the period of the orbit changed, and then others who from the DART team who do the modeling of what might happen once DART impacts Dimorphos, use all of that information as well as any properties that are known about the asteroid from the cameras, as was mentioned, from other ground-based observations, and putting all of that together to have a better understanding of what happened. And yes, all the modeling states this will be something that's measurable from the Earth, and so this is kind of a cool partnering between a spacecraft team and ground-based astronomers, and it's really exciting to see how this will all play out.
So Moshe Malik on Facebook asks, what are the chances that altering its course today will not make it hazardous to Earth in the next 100 years or so?
Well, and that's what's so nice about this particular asteroid system. It's not a hazard to Earth, and it's not going to be in the future, and we couldn't even make it a hazard should we want to. And so, which we don't want to, but we can't. And so that's why it's a really good laboratory for this test, to have this binary asteroid system come within a distance to Earth where it can be safely observed from the Earth, and do this test at the same time. So it's really actually a unique opportunity that nature has given us in a nice setting where there is no hazard to Earth. So it's perfect.
It's good to hear that Dimorphos Dart's target is not a threat to Earth. So, Ender Resting on YouTube asks, could you tell us more about Dart's solar panel arrangement? Does the offset arrangement help it navigate better?
It's interesting. I'm not exactly sure how to answer that question, but these are fascinating arrays, these rollout solar arrays that have been used on the International Space Station. And so this is a neat opportunity to take a tested technology and use it now on a spacecraft. And I don't think that their placement is important, except that they just need to not be in the way of the instrumentation on DART. But this is a neat chance to utilize this technology that's already been used on the International Space Station.
So Kelly, we have time for just one more question, and I'd like to end with your career, because your career at NASA sounds so interesting. And for anyone listening today, what was your path like in your current career, and what advice would you have for someone wanting to pursue something in planetary defense?
Well, I was a research astronomer at Goddard Space Flight Center before I came to NASA headquarters and became more of a bureaucrat. But the nice thing is now I'm in this position where I can support some really fantastic people and help to manage a program that keeps all of these efforts going, finding asteroids, following them, characterizing them, calculating orbits. And so it's a real privilege to get to do that and work with some really fantastic people and support them. And so science is a route. I was an astronomer. There are people, engineers who are involved on the DART mission and scientists. But I must say, to work in planetary defense and at NASA, I always say if it's just scientists and engineers, we'll be in big trouble. We need all kinds of people, budget people, public affairs people. We need lawyers and policy people. And I mean, so there's so many ways to support any field. And so it is possible to pursue your passion and also be involved in something like planetary defense or other activities in NASA.
Well, Kelly, thank you so much again for joining us today and for everything that you do at NASA. It's been a pleasure.
Well, thank you, Josh, and for all you do too.
And thank you all for watching at home. You can keep up with the DART mission on social media by using the hashtag DARTmission. And you can also follow NASA's solar system on Twitter, Facebook, and Instagram. You can keep up with NASA's Planetary Defense Coordination Office and asteroid-related efforts on Twitter by following Asteroid Watch. And for the latest news on DART, visit www.nasa.gov/DART. Make sure to watch the DART launch, currently scheduled for November 24th at 1:20 a.m. Eastern Time. Thank you so much again, and keep looking up.